Good morning. Today I'm Saritha Kumari, Triple E, Department Assistant Professor, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today the topic is testing of insulators and some other numerical problems. So the topic is mapped to course outcome 2. So first testing of insulators. So the according to British standards, the electrical insulator must undergo the following tests. There are three tests. An insulator, a designed manufactured insulator, should undergo. The first one is flashover test. Okay, then second performance test, and third one routine test. We'll see one by one. Flashover test. So what is this flashover test? See that in this they apply the voltage on the insulator. They apply voltage to the insulator and they will see the voltage at which we will get the flashover. Okay, the voltage at which we will get an arc. Okay, through the insulator. So see that under this there are three types of flashover test. There are three types of flashover test. So first one is power frequency drive flashover test. First one, power frequency drive flashover test. So in this what they do is they apply the voltage. Okay, they apply the voltage to the insulator at normal operating frequency, that is 50 hertz. Okay, and they will see at which which voltage there will be a flashover. At which voltage there will be a flashover. So they will note down that flashover voltage. Okay, that is a power frequency drive flashover test. Okay, now the second one, power frequency wet flashover test. Power frequency wet flashover test or rain test. They also say it as rain test of insulator. So in this what they do is water is sprayed at an angle of 45 degrees. Okay, so they are doing the power frequency test with wet conditions. Okay, that is the only thing. So here what they do is water is sprayed at an angle of 45 degrees. Okay, over the insulator in such a manner that its precipitation should not be more than 5.08 mm per minute. Okay, that is how they spray the water. Okay, so now and then at the same time they will apply the voltage. Okay, apply the voltage at operating frequency 50 hertz under this condition, and they will see at which voltage, okay, which value of voltage there will be a flashover. And third one, impulse frequency flashover voltage test. Impulse frequency flashover test means here an impulse voltage is applied, means voltage at very high frequency. Here it is mentioned as several hundred kilohertz. Okay, so voltage with operating frequency of several hundred kilohertz is applied. Okay, and they will note down at which point the spark occurs, the flashover occurs. Okay, so that is a impulse frequency flashover voltage. Now here they will define a ratio which is called impulse ratio, that is defined as impulse frequency flashover voltage by power frequency flashover voltage. Okay, that is how they define the impulse ratio. Okay, and this value is given as 1.4 for pin type insulator and 1.3 for suspension type insulator. Okay, so that is how in general that is the value should be 1.4 for pin type insulator, 1.3 for suspension type insulator. Next, second type of test, performance test. Okay, under this there are four types of tests are there. So first one, temperature cycle test. Temperature cycle test of insulator. What they do is they first heat the insulator in water at 70 degrees Celsius for 1 hour. Okay, they first heat the insulator in water at 70 degrees Celsius for 1 hour, and then immediately they cool down to 7 degrees for 1 hour. Okay, so first it is heated for 1 hour, then immediately cool down. Okay, to cool down for 1 hour. Okay, then they repeat it for 3 times. Okay, observe, and they observe after 3 times. After 3 times of doing this, they observe for glazing and also no deterioration. Okay, that is how this is done. They check for is there any deterioration, okay, or glazing. So there should not be any deterioration, okay, or glazing. So that is what this test, some temperature cycle test. Next, second one, puncture voltage test. Okay, puncture voltage test. What is this puncture voltage test of insulator? Are they telling it as destructive test also? Insulator is immersed in insulating oil and a voltage of 1.3 times of flashover voltage is applied. It is immersed in insulating oil and a voltage of 1.3 times the flashover voltage is applied. Okay, and they and they should and there should not be any puncture. There should not be. So that is how this test is done. So they immerse the insulator in oil, insulating oil, and 1.3 times flashover voltage is applied, and there should not be no puncture. Okay, that is the puncture voltage test. Next, porosity test. Porosity test of insulator. What they do is insulator is first broken into pieces, and then these broken pieces of insulator are immersed in 0.5% alcohol solution of fusion dye under pressure of about 140.7 kg per centimeter square for 24 hours. So for this porosity test, they broke the insulator into pieces, and these pieces are immersed in alcoholic solution, 0.5 alcoholic solution of, okay, fusion dye under pressure. Okay, what is the pressure here? They mentioned 140.7 for 24 hours, and after that they observe for penetration of dye into it. So they will check for any penetration of this, okay, alcoholic solution into the, okay, into the insulator. This test indicates the degree of porosity. Okay, this test indicates the degree of porosity. So there should not be any penetration. Okay, that is for a good insulator, there should not be any penetration of the dye. Okay, so this is a porosity test. And the next one is mechanical strength. Mechanical strength test. Mechanical strength test, in this what they do is insulator is applied by 2.5 times the maximum working strength for about 1 minute. Okay, 2.5 times the maximum working strength for about 1 minute. Okay, then this test determines the they apply that for 1 minute, and then this insulator should be withstand that. Okay, so this determines the ultimate mechanical strength. Okay, so this test indicates the ultimate mechanical strength of the insulator. Next, third type of test, okay, routine test. Routine tests. So under this we'll see there are three, okay, there are three tests. First one, high voltage test. High voltage test, insulator is inverted and placed into water up to neck, okay, and a high voltage is applied for 5 minutes. Okay, high voltage test. It is insulator is inverted and placed in water up to neck, and a high voltage is applied. for 5 minutes. Okay, so it has to withstand that. So that is how a good insulator should be. Okay, then proof load test. Proof load test of insulator. A load of 20% in excess of specified maximum working load is applied. Okay, a load of 20% in excess of specified maximum working load is applied for about 1 minute. So that is okay. So that is what they do in this test. And then third one, corrosion test. Corrosion test of insulator. The insulator with its galvanized or steel fittings is suspended into a copper sulfate solution for 1 minute. Okay, so insulator with its steel fitting or galvanized fitting, it is suspended in a copper sulfate solution for 1 minute. Remove and clean and repeat the same for 4 times. Okay, they what they do is they repeat it for 4 times, and there should not be any metal deposition. Okay, there should not be any metal deposits on it. That is a corrosion test. They check. That is how. So these are the test. Okay, these are the tests they do usually on the insulator. Okay, so there are few numerical problems. We'll see. See the first problem here is, see that it is given a line of each line of three-phase system is suspended by a string of three similar insulators. If the voltage across the line unit is 7.5 kV, calculate the line to neutral voltage. They have given voltage across the line unit, means they have given the unit that is near to the conductor, right? That is called line unit. Okay, so that is V3. That is nothing because they have given three similar insulators. String is having three similar insulators, means the total voltage V is divided into, there are three insulators, so three voltage is divided into three parts, V1, V2, V3. So V3 is given as 17.5. Okay, calculate the line to neutral voltage. They are asking system operating voltage. Assume that the shunt capacitance between each insulator and earth is 1 by 8th of capacitance of insulator itself. Okay, it is given. That means they have given the what is that given shunt capacitance between each insulator and earth is 1 by 8th of capacitance of insulator itself, means shunt capacitance. So that is what we have the definition of a factor K. Okay, a factor K that is defined as, okay, ratio of ratio of capacitance between insulator and earth to self capacitance of the insulator. So that's why K is given as 1 by 8. Now, in the question, they're asking string efficiency also. Also find the string efficiency. So what is given data? It is just given the string with three units, three insulators, and they have given V3 17.5. Okay, and K is given 1 by 8, and they are asked to calculate the system operating voltage, phase voltage, and also the string efficiency. So based on the given data, okay, so we have to first draw the figure. You can see on the right side. So here this is a metal cross arm, right? This is a pole support, right? So now there are three units, right? And the down string, on the end of the string we have a conductor, right? This is a conductor. Now there are three units, right? 1, 2, 3, right? 1, 2, 3. So the voltage V is divided into V1, V2, V3. So now if we say C is the self capacitance, okay, C is the self capacitance of each insulator, okay, then automatically the shunt capacitance, okay, between the insulator and earth. This is the, okay, support means insulator between the sorry, capacitance between the insulator and the this is nothing but a earth. Okay, this is support. That means we can take it as, because support is placed on the earth, on the ground, we'll say that this is the earth. So it is given because we have the ratio K is given by shunt capacitance by self. So because we have taken this is C, so what is this? This will be, we can say it as K into C, right? K into C. So that's why it is denoted like this. Now, okay, to solve the problem, we know how to start. Take the currents in the insulators are capital I1, capital I2, capital I3, and currents in the shunt capacitances are small I1, small I2, small I3, and the junctions are nodes. Okay, the point between the two units. So if we say this is a first insulator, unit 1, second insulator, between them the point is, we say it is it as say it as, okay, node A, okay, first node. So let us say this is node A, then between 3 insulator 3 and insulator 2, the point is B, the, okay, junction or node is B, and the last one between the conductor and this shunt path, the point is C. So now we know how to start, because we have done similar kind of not exactly similar problem, but we have done one problem in the previous lecture also we have seen. So initially we write the given data, that is what it is shown here. Okay, now first junction, at first junction A, writing KCL. Okay, so sum of incoming currents is equal to sum of outgoing currents. So what is the incoming current? What are the incoming currents? See here at point A, junction A, it is only I2. Okay, so capital I2 is equal to, the remaining two currents are leaving currents. So capital I2 is equal to capital I1 plus small I1. Okay. Now write down that in terms of currents, in terms of voltages and capacitance, because we know that in case of capacitor, V is equal to I by XC. That means XC is nothing but V into omega C, right? So if we neglect the imaginary J parameter, because all our capacitance is only in the problem, so write only in terms of V and, okay, C. So I2 is given by, what is the current across that capacitance? The voltage is V2, right? So V2 into, what is the capacitance? C, right? Its self capacitance, V2 into omega C, and V I1, capital I1 also the same manner, V1 into omega C. And what is the small I1? So here capacitance is Kc, right? And the voltage across this point, and this point is nothing but this point only, right? This point is nothing but this point only, that is V1. So V1 into K omega C, right? So now cancel the similar term, omega gets cancelled on both sides, C also gets cancelled. So V2 is equal to V1 into 1 plus K. Okay, V1 into 1 plus K. Because we know K value 1 by 8.125, substituted here. So V2 is given by 1.125 V1. Okay, now next set junction, next junction B, similar manner, if we write capital I3 is equal to capital I2 plus small I2. Okay, so capital I3 is nothing but current in the third unit, down unit, V3 into omega C, small I2, capital I2 is V2 into omega C, small I2 is nothing but what? Small I2, okay. Small I2 is nothing but this is, right. So the voltage between this point and this point is nothing but voltage between this point and this point. So V1 plus V2, right? So V1 plus V2 into K omega C. Okay, that is small I2. Okay, now cancel the similar terms. We'll get V3 is equal to V2 plus in brackets V1 plus V2 bracket close K, because we already know from the previous equation V2 in terms of V1, that is 1.125 V1. So V3 is given only in terms of finally V1 1.39 V1. Now because it is given in the problem, V3 is given 17.5 kV, right? So calculate from this, we can calculate V1. Okay, so V1 is calculated. So V3 by 1.39. Okay, so finally obtained as 12.59 kV. Now, because we have the V1 value, so V2 because we have a relation between V2 and V1 from the junction A equation, V2 is 1.125 V1. So substitute there and also calculate V2. So finally we have all the values. V3 already given, V1, V2 calculated. So finally, according to the given question, they ask you to calculate the voltage. Okay, system line voltage, system operating voltage. So which is nothing but V is equal to V1 plus V2 plus V3. Okay, so that is the phase value. That gives the phase value of the system. So that is given by all values substituted and 44.25 kV. 44.25 kV. Finally, efficiency is given as, okay, we know the efficiency definition, voltage across the bottom unit over, okay, number of bottom voltage across the bottom unit, means here there are three strings, right? So units, V3 by small n number of strings into voltage across the uh, sorry, in the numerator this is the total operating voltage. So system operating voltage, okay, so in the numerator and number of divided by number of strings into voltage across the bottom unit, that is V3. So total operating voltage, what is V? 44.25. So that is substituted and down, and V3 into V3 is 17 per substituted, and finally efficiency is calculated. Next, so there is one more problem here. So a line of three-phase system is suspended by a string of three identical insulators of self-capacitance C. So it is given the string has three insulators, and each insulator self-capacitance C, and shunt capacitance of connecting metalwork of each insulator is 0.2 C to earth and 0.1 C to line. They have given shunt capacitance value, but they're given in two values. They're telling each insulator, okay, shunt capacitance of metalwork to, okay, earth, okay, metalwork to earth means we know that. So drawn in the diagram, you can see. So that is given this one 0.2 C and 0.1 C2 line. The telling shunt capacitance of each metal work, okay, of a insulator to line. So we know that we have a concept for the uh, if efficiency improvement. We have seen there are three methods. Under that, one method is, okay, guard ring method. Okay, so in that, what they do, they connect a guard ring, a metallic disc, okay, around the conductor. This introduced metallic disc introduces another shunt capacitance, new shunt capacitance into the system, that is introduced between the this metal link and this line, and this line conductor, and this metal link, metal work, right? So that is what it means. So that is given that capacitance 0.1 C. So these other side capacitances are 0.1 C. Let's see. what is this 0.3 ct? Well, what else they have given in the problem? Calculate the string efficiency. They are asking efficiency. If guard ring increases, the capacitance to the line of metalwork of the lowest insulator is 0.3 c. Okay, it is a specific given the lowest insulator shunt capacitance is increased to 0.3 c. Okay, so initially they mentioned they have zero point 0.1 c only, but the lowest one they are telling it is increased to 0.3 c. Okay, so according to the given data, so the diagram is drawn system. Okay, the insulator is shown with 3 units. So now what they ask, calculate the string efficiency. So here the same manner like previous problem, we solve the problem. Okay, only the additional, there is a one more additional current comes at each junction. Accordingly, we'll get the equations, okay, and accordingly we'll solve the problem. Okay, so it is just a step by step solution, solving the mathematical equation only. There is nothing new. So here that is what it is okay, shown. So first see that first the currents are marked. Okay, if a guard ring is there in the system. Okay, so we know that that is explained in my last lecture. If a guard ring is connected in the system, what it will then what will be there? So see that there will be a new capacitance introduced like this, right? And accordingly, new current which opposes the exactly this left side current, equal and opposite. So that is what we want to eliminate this capacitance effect. Okay, shunt capacitance effect, left side shunt capacitance, so that we will finally get the uniform voltage distribution across all the units. So good efficient 100% string efficiency. So now we'll see at okay, first current is in the metallic guard ring current is small I1 dash, right? That is equal and opposite to this small I1. Similarly, the down one I2 dash. Now at point A, at junction A, apply KCL. So what are the incoming currents? Capital I2 and small I1 dash. So that is equal to sum of those two equal to leaving currents capital I1, small I1. So that is what it is written. So then substitute in terms of voltage and capacitance. Capital I2 is given by V2 into j omega c, and small I1 dash is given by, okay, so small I1 dash is given by, what is the voltage across this? V2 plus V3, right? Small I1 dash is with respect to conductor, it is connected from the line conductor, around the line conductor. So what is the voltage? V2 plus V3 into point 0.1 c, 0.1 c. Next, small I1, capital I1, as we already know how to write those. So after solving, the equation is V3 is equal to 12V1 minus 11V2. Okay. Now, next junction, at junction B, writing KCL again, capital I3 plus I2 dash, small I2 dash is equal to small I2 plus capital I2. So what is capital I3? V3 into omega c plus capital small I2 dash is given by, small I2 dash is given by, that is what is I2 dash? Starts reference is conductor, right? So this point and this point. So V3, right? So V3 into 0.3 C omega and is equal to capital I2, small I2 is written in terms of V voltage and C. Next, so after solving, the equation is obtained. 1.3 V3 is equal to 1.2 V2 plus 0.2 V1. Now we want to simplify these equations. Finally, we will get the string efficiency. So what we do is, in this equation, from equation 1 substitute this V3. Okay, substitute for this V3. So that is what it is shown. So finally we'll have V2 in terms of only V2 is given by 0.993 V1. Now similarly in the same manner, use the previous same two equations, write V3 in terms of V1. Okay, so that is what it is done. Next step, put V2 in above first equation. So V3 will is obtained as 1.077 V1. 1.077 V1. No, so now finally V2 we have in terms of V1, V3 also in terms of V1. Finally, the voltage, total voltage is given by sum of V1, V2, V3. So V1, okay, plus V is equal to V1 plus V2 is 0.993, V1, V3 is 1.07 V1. So finally that is 3.07 V1. So that is how, okay, total voltage is obtained in terms of V1, because finally we want to calculate string efficiency. We have a definition for string efficiency is total voltage by, that means system operating voltage, that is nothing but voltage between conductor and earth. Okay, so over number of units into voltage across the bottom unit. So here what is the bottom unit? V3, right? So V3 we have in terms of V1 1.07 V1, and total voltage also in terms of V1 3.07 V1. So that we can calculate, we can cancel V1 in both numerator and denominator. So finally that is how string efficiency is calculated here, and it is obtained as 95%. It is obtained as 95%. So this is how the with a guard ring connected in the system, um, problem is solved and string efficiency is obtained. Okay, this is the problem, and the problems, these two problems are taken from the book, second book, VK Mehta, Rohit Mehta, Principles of Power System. Okay, and testing of insulators topic is from the test book, first test book, CL Vadba Electrical Power System. Okay, so this is a lecture for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.